Will it in the year? Not in the aisles, fire hazard. Okay, so our next speaker is Percy who is just sort of down the road on here. He's a PhD student?
Yep.
In the Centre for Software Assurance, and he's going to talk to us about a model-based approach for testing of open source. All right, take it away, Percy. Thank you.
Thank you, James. Yep, sure.
Eventually we'll get this right.
Okay, that's fine. Good afternoon, everybody. As James said, I am a PhD student at Bond Uni, and we work on more on the software engineering side. We work with testing, and especially with model-based testing. And as happens on every or to every PhD candidate, someday the supervisor comes and say, okay, I have an idea that we can apply what you are doing to something related or something else. And actually my work is on model-based testing. But my supervisor came and said, okay, I was thinking that we can apply that to operating systems, to kernels or modules in operating systems. I would say generally model-based testing is a technique, it's a black box technique that is very good for high level, for you to define a high level specification of your requirements in a kind of formal way, but still it's high level. And as far as I know, most of the development in kernels and operating systems is very low level. So they said, okay, we have a problem there. But then we started to see what we can do for applying this approach to the testing of operating systems. And we come to these conclusions. This is an ongoing project because there is somebody else at uni that is taking over that to make it, to apply this approach to a whole range of modules in a kernel or in an operating system and see what we can achieve. Well, as I said, the model-based testing is a black box testing approach that focuses on functionalities, not on the code. Okay? Although we can say that every piece of code is a model. It's just a low-level model, but it is a model. So we can talk about models in different levels of abstraction, and the same concepts will still apply. But being used as a black box approach, we discovered that we don't need, or we do not require the knowledge of the internals of the kernels to test them. Okay? We can test them from a system perspective where we pick one module, one function, and we say, okay, the role of this function is doing X and Y and Z things, and then we apply that function, and then we assert or we try to see if that goal was achieved by the function. We saw that the testing on some of the modules, for example, we went to the storage community, and then we saw that there are some tests available on the internet. The test suites they use are available on the internet, and we saw that these test suites are basically based on the scripts, and those scripts, what they do is call some modules of the operating system and then see if the operating system said operation successfully done or not. And then this approach is used also in certification. So If you want to certify that some testing, that some kernel module comply with some standard, then you have a set of test cases where you apply that test cases to your particular implementation, and if those test cases are passed, are satisfied, then you say, okay, I'm compliant with that particular standard. However, it has two problems. This approach has two problems when how it is applied now. The first one is documentation. For standards, there are a lot of documentation for the test suites, so usually that's not a problem. But when we went to the storage community on the Open Solaris community page, we saw that there was too much documentation. If we don't know anything about kernels or storage drivers and these things, it will be very, very difficult to understand what this thing is doing. So that's the first problem. And the second problem was flexibility. We're going to see that once you have your script, your test case as a script, then you run it once and twice and everything is the same. And which means that the people that is writing those scripts have to think about all the possibilities that can happen, and that is almost impossible in any software development. You know, there is always somebody that will use something that was not developed to that use, and will break the system. So you have to think about a lot of possibilities that are not on the scripts. And we saw that on the Open Solaris testing. It's based on the scripts, and it's based on a normal test suite where you have some test scenarios, and inside the test scenarios you have some test purposes. So a test suite is divided in test scenarios and test purposes. And for each test purpose, usually you have one script that performs some operations and do some assertions. However, when you go and analyze the scripts that are available for the storage community, most of these scripts are independent. What do I mean? You can run one script from the beginning to the end, and it has a lot of, it has a sequence of operations, but the first operation is always preparing the environment, and the last operation is always cleaning the environment. So anything that happened in this sequence is forgotten for the next execution, which is good on some tests. I mean, if you want to control your test scenario, that's good. But what happens on a system testing? Sometimes you don't want to forget what happened before. That doesn't happen on a system. When the user is doing something and crashes the system once, and the system does not clean itself magically. Hopefully it does, but sometimes those errors come to the next session, or they are persistent on the system, and then those errors will provoke some other crashes, and still the system will degrade itself as it is used. So we didn't feel so comfortable with that thing of okay, clean the system after each use, and the test purposes also are not fine-grained. I'm going to show you later that, but the idea is it has too many operations in a sequence where you can, on our opinion, you can just split it up in several operations and then do all the combinations, not only one sequence of combinations, but more combinations to see what happens with the system. Maybe I started on the wrong way. I talked about Open Solaris, how it's tested, but I'm trying to apply model-based testing. What is model-based testing? model-based testing is just the use of some kind of model, usually some kind of formal model, to derive some test cases from it, and then apply that test cases against the system under test. The most popular models you have are basic automatons. Okay, you have states and you have actions that occur. You have actions in the system that occur, and then they provoke the system to change from one state to another. So you have actions and states. But that's the model. Then how does relate that with the system under test? Well, you have a test harness, which is usually a script that understands what the model wants to do and then translates to the system under test to really call to functions in the operating system to execute them. The good thing of model-based testing is that you can perform an interactive approach where you don't need to write the script and then say, okay, execute that, let's see if it passes or not. It's just execute this function and then execute the next one, and what happens if I execute the next one? So you can work on in an interactive fashion, interleaving the generation of the next action with the execution and see what's happening in the system on the mean, in each part of the execution of your script, of your test case. The problem with model-based testing is the cost of the testing, because you should usually you need still to write your scripts to go to the to communicate with the system under test, but you also need to model the system, and usually modeling is not an easy task. Okay. So that's the usual architecture of model-based system, or a system that performs model-based testing. You have the models that are fed into a tool, a testing tool. This tool understands the model on a module that we call the generator, and then produces an action that is going to be executed, and it sends it to the adapter. The adapter is the script that understands how this action actually is performed in the system under test, performs that, and then it can observe what happens in the system and go back to the tool and telling the tool, okay, that was the response of the system, and check with the model if it is okay or it is not. Okay? So what we did to apply this approach to OpenSolaris for, yeah, I should say OpenSolaris. Is that right? It's not Solaris, it's OpenSolaris. Anyway, what we did is, first we have to create an abstract model of the operating system, but only of the components we are testing. Okay? We don't care about the rest of the system. We can isolate one module and say, okay, we are testing the file system, and the file system has some actions, particular actions that will affect particular objects in the system, and that's what we model. So we have, for example, a set of available disks, a set of partitions of on each disk, some directories or mount points to mount these file systems, etc. Files, and the actions those are the objects, and the actions that we can perform on this file system module are, well, we can format the disk, we can create a partition, create a file system. Create a partition again. But we can also represent a sequence of action as an atomic action as the current scripts do. So what we did is try to compare two approaches. One is using model-based testing just to drive the execution of the current scripts, okay, and analyze what happens. So what we did is we took the scripts on the web, and then we made this model, and the actions on the model actually corresponds one-to-one to each script in this test suite. In this approach, the advantages of model-based testing that I said, we can test all the possibilities and see what happens if we change some of the we change the next action for another one, are lost because what the scripts do now is clean the system, run the script, clean the system again, so that no change is carried to the next execution of a test purpose, of a test suite. However, only the fact of building the models gives us the possibility. It's like a reviewing. It's like a reviewing the code. You are reviewing the code of the scripts, and it gives you the possibility to find some bugs. And actually, we did find one of them. I'm going to talk about that later. What we can do with this linking model-based testing with the scripts is just mix the test purposes. Or what happens now is when you want to, you have a new release, for example, you get the whole test suite and say, okay, run the test suite against the new, the current build, and then it should pass everything. What we can do with this, with the model-based testing approach is to just mix the test scenarios and say, okay, do not run them in sequence. You change the sequence and mix them in some way. It was useful because although most of the scripts clean the system before and after the execution, some of them fail on that. So some of the scripts were not good enough cleaning the system, so some states remain changed. So some changes remain to the next execution. So the main problem, and you can see, this is the graph we generate for the execution of our test cases. The test cases are called new FS, new file system 1, new file system 2, or fdisk 1, fdisk 2, because those are for each one of these, for formatting this, for fdisk, for example, there are 4 test purposes on the suite. For the new file system, there are, if I don't remember, it's 5, sorry. So you can see how they can be combined, and some of the states, or better, the system change some states between one and other execution. And in some cases, for example, this state 6, most of these format and this new file system, they do not change the state. They just clean, and that's all. So there was one thing that we saw that was a problem, because the test suite is already defined on a test framework, and this test framework, what it does is traps the error. So once there is an error, it is reported and it is trapped and it is sent to a log. While we were using that script and our tool never reported an error, and we said, okay, that's, well, the system is so good, or there is some mistake there, there is some problem, and we realized that the errors were trapped in the middle by using this script. So we needed to do some realistic example. We needed to get rid of this trapping and try to make it more fine-grained to see what happened. And then what we did, so what we did is we divided the scripts into very, very atomic operations. So one of the scripts were creating extend EFI label on a system, and then creating some file system, UFS file system there, everything together. So we separated that. We create the labels first, then we create the file system, then we mount it. So we did that separation, and the idea was to do like something like that. Okay. On the beginning, we have our new file system action. That's one script on the current test suite. And that script, if you analyze that, has one operation that is called format fdisk SMI, creating a SMI label on the disk. Then it adds a partition, then creates an UFS, and then it mounts it. So that's the whole sequence. And we realized, well, we can do something better. We expect it to be better, and we can say, okay, fdisk is one operation, then add partition and delete partition. There are two operations there, and we can add the partition and delete the partition many times and see what happens. See if the disk or the system gets tired of doing it in some time. We can create the file system and then delete the partition and see what happens. Does it allow it or not? Of course it does. And then mount the file system, and there is an arrow that you cannot see there, but if we try to delete the partition when it is mounted, of course it will not do anything to the system. It's an error. It will not be allowed to do that, so the model stays there. So that was our idea, and we did it for the file system test purpose. So including some format fdisk commands with the edges corresponding to actual commands in the operating system, and in some cases we didn't consider the data generation, the parameters generation, because it was kind of I was not used to OpenSolaris, and then the naming of the devices was quite difficult to me, and the slices and partitions, and so we try to simplify that. But there are some parts where we actually generate data, getting some information from the system to the tool. And what we achieved, it's not the complete state graph, but you can see that there is a lot more of possible executions of actions, and of course there are a lot more states on this execution. So it's probable that most of them, or some of them, will not be so relevant or repetitive. But if you try this approach on a, during the night, or if it is fully automated, you can let it run a couple of hours, and it will get crazy and do everything it can, as several users will do, and then try to break the system. And that's the idea of testing. So I'm going to show you the tool working on my OpenSolaris virtual machine. The tool is a tool that is created by Smart Technologies, or KCA Ross and Associates. We work with them. Just let me start. It's a tool based in Prolog. So we had some nice time trying to make it work in OpenSolaris, but we did it. And my scripts are basically a Java server, that is a Java program that is listening to a socket and just applying that, calling the the server is initialized. I will show you the models if we have time. So first I'm going to get the model where there are these scripts as they appear on the web, on the current test suite. And I'm going to connect this to the system, and I'm going on an interactive approach. Whenever you start the system, you have to configure which disk do you want to use for testing. So I have this disk that this is the C3D1 disk anyway. I'm going to configure it. Once you configure it and it is successful, you can see here the tool says, okay, the test has passed. Then I can run the other actions that are here. So I can run the first script of fdisk or the second one. Let's try that. Of course, the tool, as I said, will say it passes. That's it. Oh, I have to select the action. It does some data generation, so I have to select which method and then which action I do want to run, with data. If I can generate more than one disk, for example, is available, I can see that. You can see that the second test has passed, and I can see the output of the other test suite that is running on the background, the one that traps the error, it's also saying that the test passed. So both of the tools are giving me the same result. I'm going now to, and then on this tool you can do, for example, a random generation, and you can try to run it randomly and see what happens. I'm not going to do the random because there are some scripts that take like 15 minutes to run, so they just dump the disk to some tables of the disk to some files. So I'm going to close that and get another model, and this is the model that we did with more fine-grained operations. And in this case, okay, I need to, because the models they share some of the variables the Prolog complains. So we use Prolog because our models are declarative. We just say, okay, the idea of the models are you have some state variables, and over this state variable you say, okay, in this action, for this action to occur, there are some conditions. These state variables have to have values in those ranges, and you put some conditions, and then you say, On the end, after this action has been executed, this action variable, this state variable should have these other values, and then you just declare which values you need in the model. Let me just show you the. Okay. In this one, I did what I showed you, trying to. Oh, I'm going to connect to the system, and then I initialize. Probably it's not. This one is not. Some of the actions on this model are not implemented. So some of them will just fail, and some of them will pass. For example, I'm going to do a directory to mount the file system, and that would fail probably because it already exists. I would try this one. Okay, so mount tier 1, because I ran it before, it exists. It cannot create it again, so it says I cannot create that mount point to be free for mounting a file system. I created another one, it passes. And then I can just, for example, format the disk with an SMI label. And let's see if it passes or... Yeah, it passes, and I can try to format the slide 0. It passes again. Probably, if I try to format the disk to EFI, I don't remember. I think it was not. Oh, that's good. Everything is passing. Yeah, actually, yeah, that's. I cannot, in my model, and I'm not sure if that is the actual representation of what happens in OpenSolaris, but I cannot format the slide 0 after I created an EFI label on the disk. Probably because the label EFI uses P0 instead of E0, S0. I'm not sure about the file system because it was very new to me. But that's what I put in the model, and then it fails because the system is not, the scripts are not running as the model predicts. So that's, I just want to show you the models. Do I have time?
You've got 5 minutes.
Okay, yeah, that's fine. So I will. Any of you, or how many of you have programmed in Prolog before? Okay. So yeah, you can see. I don't know if, I'm not sure if I can make it magnified. No, I don't see if I can magnify, but you can see there are some state bar here. It means we are declaring the state variables first. Once they are declared, I need the values, the initial values for the system. That's the usual Q0 on any automata. And then after that, I declare the transitions, and my transitions are initialized. So I said, and this, I generate some parameters for this In this case, it has no parameters. And then the transition, what it says, okay, take the values of the state variables and then compare them with some predicates. If they are true, the transition can occur. Then set the values of the state variables to a different one, and that is everything that occurs on a transition. I have the disk SMI transition. It generates a parameter that is in which disk I want to, or which disk I want to format, and then it's the same. It's get the variables, assert some predicates on them, and then change the values, and then store the new values for that state variables. It's pretty, the models are very, very straightforward. So that's one thing that is good. We try to minimize the cost of creating the models by doing that. And finally, what we have some suggestions and conclusions. As I said, this is an ongoing project where we are trying to expand this to more to other modules and see if it really works with not only format disk can create, but it can work probably in a more low-level approach inside the kernel, or still on the same approach but with another modules. And then that is the model-based. The same principles apply at different levels of abstraction. So we can do that. The only problem is that we have some trade-offs. Abstraction versus flexibility. The most abstract it is, then it gets less flexible in what combinations we can do. But if we want it very flexible, we end writing another kernel instead of, or another module instead of a high abstract model. So we have to see what is the right balance for that. And then the abstraction versus the model complexity. The more abstract it is, it's very complex. If it is only one, only one function, it executes when these values are on the variables, and the result is that. It's like 2 plus 2, it's equal to 4, and that's all. That's easy. But if you want less abstraction, more flexibility, then the complexity of your model, it becomes harder or greater. The model building leads to bug discovering. We had a problem with the current scripts of that are on the storage community test suite. There was one condition that was not right, and our tests were failing when they shouldn't fail, and of course the ones that should fail were passing. So, and we let know this to the people on the community, and we can think of this model-based approach as having a standard for not only one operating system, but let's say, okay, 2, 3, or several operating systems that want to implement the same functionality or the same standard. We can set a benchmark where the model acts as a generator for the test cases, as well as the documentation for the standard, and we can use it as a benchmark for different operating systems. And we don't have to think about new scenarios. The model can think of them instead of us, or we can think, in terms of the model and modify the model, and the model will discover new scenarios if it is possible. So that's the end. If you have any question or any comment.
Have you found any bugs in the kernel with the framework?
Not in the kernel, or I'm not confident in saying the bug is in my model or is in the, because that's the problem when, you know, well, the other thing is to apply this approach, you need a modeler, somebody that can, you know, type the models or write the models, and you need an expert on the system that tells you, okay, that is how the system have to behave. Yeah. But we found that bug on the scripts, so I don't know. Yeah.
Do you think about using any other tools than Prolog? I mean, similar sort of modeling could be done in, say, a business process modeling tool or something like that. It might be a bit more portable, I don't know.
Yeah, we can use, I mean, the approach is the same. We can use different tools. That shouldn't be a problem as long as we can write the models and express. We can use, there are some set or B models that they use in France. As long as it has the expressive power to tell us values and the results of some actions, yeah, we can do that. Yes.
We've got time for one last question.
Have you applied any second level analysis to the models themselves so that you've got coverage on the script?
No, we haven't. We can, because there are some coverage reports on the tool, but we haven't worked on the basis of coverage in the models, because the models are pretty basic and that kind of handcrafted. We got coverage of all the scripts when we did that approach, but not on the one that was fine-grained. We didn't analyze that. Yeah.
Well, thank you very much, Percy.
Thank you very much. Okay. Oh, thank you very much.
Right.
Okay,
And
let
our next
me-
speaker is Pavel, who has travelled from the other side of the planet